Hello, I have decided to use Linux as my topic of OS for my research project, and the three topics that I will be sharing today are CPU scheduling, input-output management, and file systems. Number one, CPU scheduling. The main focus of CPU scheduling is how OS allocates CPU time to a process to complete its job. Okay, so let's straight jump in. Linux scheduler. As you have learned in class, CPU scheduling is how the OS allocates CPU time to a process to complete job. The job of the scheduler is to control and decide which process will run next among all processes that are in the runnable states. Linux has its own version of scheduler. The main goals of the Linux scheduler are control and decide which process will run next among all processes that are in the runnable state, maximize multitasking, maximize resource utilization, make sure CPU-bound processes do not starve, and the final trait is that Linux schedulers favor I/O-bound over CPU-bound processes. At the end of this section of my research on Linux, I will tell you why. So to continue on Linux scheduler, Linux implements a preemptive style of scheduler. As we have learned in class, there are two types of schedulers, preemptive and emptive. Preemptive is when the scheduler is able to interrupt the process to swap in a new process. The processes are preempted based on a value known as priority. Linux implements priority-based scheduling algorithm over first come, first serve. So as I have explained, the value of property plays a big role in how processes are picked by the scheduler. Processes with a higher value of priority will be scheduled to run first. Linux scheduler is time-based rather than job-based. So what does it mean when it's time-based? CPU time is divided into slices or quantums for each process. It means that Linux scheduler will preempt the process based on certain time measure. Sounds familiar? You will see round robin that we learned in class implemented in Linux schedulers. So first of all, priority. Priority is a very big topic on terms of CPU scheduling in Linux systems. Priority is a value associated with each process. Linux scheduler classifies processes into different types, which will have a different priority level. These different types or class systems of the process determines its priority. Linux scheduler calculates priority dynamically, meaning that it can change. So now that we talked about priority, let's talk about a little about processes in Linux CPU. Classification of processes. Not all processes are the same. Linux distinguishes every process into three major types, depending on the type of job or state they are in. Furthermore, on top of classification, there's also direction of processes, or also known as bound. Processes are bound to a certain direction. There are two types of bounds. First of all, let's look into classification of processes. So the three types of classification of processes are: first type is interactive process, second type is batch process, and third type is real-time process. We will look at each type in a little more detail. Interactive processes. There are processes that spend time with the user, or to be clear, spends time waiting for the user. They spend their time waiting for user input or action. An example of interactive processes that we see when using Linux are the command shell, text editor, and GUI. As you can see, these are all types of jobs that require an action from the user to continue its functions. Batch processes. They are known as background run processes. These are the processes that require no response or additional action from the user. They are merely submitted from a queue of processes and not associated with the command line like interactive processes. Examples of background processes are compilers, database search engines. As you can see, there is no action need to be done by the user. Compiler or database search engines can run in the background while it's looking for or trying to complete its goal. Third type of processes are real-time processes. These are processes that must run ahead of the other two types of processes, higher priority than all normal processes. Real-time processes require a rigid scheduling requirement. as the nature of the job must allow them to run every X time unit and complete a certain number of jobs during a span. For example, video silent applications and elevator interrupt controllers. What would happen if an elevator interrupt controller was not real time? Think about the madness and anger of the people living in that apartment unit. Now that we looked at the three types of classification, let's look at the directional processes, otherwise known as bound. There's two types, I/O bound and CPU bound. I/O bound processes use I/O devices. They spend most of their time waiting for I/O operations to complete. Linux scheduler favors I/O bounds over CPU bounds. Why though? Let's find out in a minute. Back on the topic of bounds, CPU bound. They use CPU computation. It's number crunching. So what? Why does these matter and have anything to do with CPU scheduling? Well, let's all put it together. All above classification lets Linux scheduler know what the processes are doing. As I said, remember that each type of process is just a regular processing doing different jobs. A regular processor, sorry. So remember priority, the value that determines when a process goes? That value is directly tied to the type of process. Batch, interactive, and real-time have different ranges of priority values in which they could have, pretty much limiting the order and priority by the class types or the classification types of each process. Now let's look in detail priority range, which is related to priority level and priority value. So priority range is the range of priority value a process could have. Normal processes, which include interactive and batch, will have a different range compared to real-time processes. Now, before showing you the formula, I need to explain about a value known as nice. Nice is a value that each process has and ranges from -20 to 19. These are the values that a user could change to affect priority of normal processes. As you must know, nice is a value that is acting on the user space. So the command to change nice is literally the command nice. As a rule for Linux, only a root user can make a process less nice. Think about it. What if every user has the ability to make their process have higher priority? That would be chaos as well in managing the system. All right, so now let's get into the priority level calculations, the nitty gritty. For normal processes, like I said, interactive and batch processes, priority level equals 20 plus the value of nice. So for example, let's say a process has a nice level of -20, the lowest it can go. That means priority level equals 20 plus -20, which equals priority level of 0. Like I said, remember that lower the priority level, higher the priority. For real-time processes, the calculation is a little bit different. For priority level for real-time processes, it's -1 minus RT priority. RT priority is a value between 1 to 99. RT priority is a value that only real-time processes will have. Mathematically, it's obvious that a real-time process will have a lower priority level than a normal process. If real-time process is not finished, non-real-time processes will not be scheduled unless all real-time processes are blocked. Like I said, real-time processes have the highest priority. If a non-real-time process exists, but if a real-time process is not finished, then the non-real-time process just must wait until the real-time processes are blocked. Now, let's look at schedule policy. There are main schedule policies that Linux uses. Different types of policies, which are scheduling classes or types of scheduling, are used on different types of processes. Like I said, the three types that we talked about. Different values for different policies are used, which implements different types of algorithms to schedule the type of processes that they're responsible for. So now let's look at some of the different types of schedule policy that are common in Linux systems. We have sched_other, which is for normal processes, and as of Linux 2.6.23 uses completely fair queuing. Schedge_batch, which is for normal processes and just use batch jobs. Schedge_idle for normal processes and is for background jobs. Now, the two scheduling policy that deals with runtime processes are schedge_FIFO and schedge_RR. They are only used for runtime processes, and schedge_FIFO implements first in, first out, whereas Schedule implements round robin. We will look at these in more details. So now Schedule FIFO. In Linux, FIFO, or first in, first out, is based on the order of process that entered queue. If no other higher priority real-time process is runnable, process continues to use CPU, even if other real-time processes with same priority are runnable. This means that Schedule FIFO is non-preemptive. Schedule RR incorporates the round robin algorithm that we learned in class. Round robin uses a fixed quantum, which is an allotted time space. Unlike first in, first out, other real-time processes with same priority will run due to the fixed time slices. To explain in details, since round robin, every process will have a chance to run, since after each quantum, a process will swap in and another one will swap out, and so on.